So we talked about our wire size yesterday because wire size is shown on the schematic. And a lot of times it's in millimeter on the schematic. So we can convert it over to American wire gauge, which is what we sell wire here in. And then also I have a chart in here, which is the wire size depending on load. So depending at 12 volts, and this is 12 volts, depending on how many amps I'm using and how long my wire is tells me really what the minimum gauge is. So as a rule, for 15 amps, we use 14 gauge wire. And for 20 amps, we use 12 gauge wire. That's a good rule of thumb. But you can see here how manufacturers get away with running some smaller wire sometimes for very short distances. So this is a chart that I put in here, going with the question you had, Alberto, about, hey, do we have this? Also, the other thing I did this morning is I resaved this PowerPoint into a new PDF and replaced the PowerPoint PDF on Canvas. So you have the new version available to you now with all the changes that we've done. So I redid that this morning. And got yesterday's video uploaded on Canvas. So you can see yesterday's class on Canvas. So I was busy this morning. So signal input. So here I have it just says throttle position sensor signal. There is ECT sensor signal and IAT sensor signal. So that input is going to vary based on the type of sensor. And we're going to get into sensors so that you'll be able to look at this. But we can see here my engine coolant temperature sensor and my intake air temperature sensor. If we look at those circuits, they're exactly the same. So they both go to ground and they both have a sensor signal. So once we learn that circuit, really, it's real easy to look at this. And we use these for transmission temperature, all kinds of things, to look at and go, oh, I know how that works and how to test it. So this right here is a sensor. And in this circuit, I have ground. So I'm going to have power up here, which means my sensor is my load in the circuit. That's my resistor. Remember, anytime we have a resistor, that's a load. And I can see here that this is a variable resistor. Here's another example of a signal input. In this case, the crank sensor. So I have a crankshaft position sensor and it goes to the computer. And this is a different type of sensor. This sensor actually makes its own voltage. And we'll learn about those also. So these are signal inputs. We also have actuators. Actuators are something that the computer uses to do something. Most actuators use electromagnetism. So what we're doing is we're converting electricity into a physical action. I'm going to open or close something. So a good example of an actuator is the door locks in your car. When you hit the button, what happens? You hear a chunk and the lock goes up, right? So we've taken an electrical signal, used electromagnetism, and we've made something physical move. So most actuators work that way. So a motor can be an actuator, relays can be an actuator, solenoids can be an actuator. We have several different kinds. So in this case here, if I want to look, the fuel pump relay is an actuator because the computer is turning it on and off. The emission control purge valve is an actuator because power is supplied and the computer is turning off the ground. Oops. Yes.
In a solenoid, can the computer read like as an input from a solenoid in case if the voltage is like off?
Yeah. So what a lot of new systems do is if I'm looking at this relay, for example, or this solenoid, we're going to have a sense circuit inside the computer, kind of like a DVOM. And it's going to look at what the voltage is here at pin 56. And it knows when it's not turned on, I should see system voltage because I have voltage coming down. It's going to come through my load all the way to my open transistor. So I'll see voltage here because I can only drop voltage through resistance if I have current flow. And we know we have no current flow in an open circuit. So as soon as we open it up, all I have is potential. So we'll see that system voltage all the way down to here. As soon as the transistor closes, Now it's going to apply ground, and ground's going to come all the way up here to the load. So now this part will have ground and this part will still have power, and my load divides the circuit. And what they do on some circuits is they put a little sense wire here. It's basically like a DVOM, and it looks, is that have power when I'm not turned on, and does it have ground when I do turn it on a ground controlled circuit? So if I don't have any power when when I'm not turned on, I might set a code for an open circuit, right? Because obviously if I'm not seeing any power there, the circuit's open. Or I might set a code for signal voltage high, meaning, or low, excuse me, meaning that I should see voltage there and I don't. So I'll get one of those two codes. On the other hand, if the computer turns it on and it doesn't see a change, then it would set a code for signal voltage high, right? Because it commanded it to go low, it commanded it to go to 0 volts, and it still sees voltage there. So the code that would be set would be circuit high. So in other words, the opposite of what it expects to see. So do all systems and all sensors do that? No. Do a lot more do it in 2021 than they did in 96? Absolutely. So it's not uncommon to see codes like this on 2005, 2008, 2012 and newer vehicles, where if I'm working on a 99 or a 2000, I've got a good chance of not seeing that. Because again, computers have become more sophisticated. I mean, just look at your cell phone. Is the cell phone do a lot more now than it did when the first Apple iPhone came out? And that was what, 2008, 2009, somewhere in there? So obviously cell phones have been around before then. So there's a big difference between a 1996 cell phone and a 2008 cell phone to a 2020 cell phone. Why? Because computer technology has changed. It's become cheaper to manufacture. Processors are faster, memory's cheaper. So with that being said, now they're doing more and more things in the computer to better analyze these systems. Great question. And we will get into that when we get into some of our circuit testing and stuff in our next section. So this is track style schematics. These look way different than what we've been looking at. These are used on European vehicles. And if you look at the bottom, you can see numbers 1 through 14 and then 15 through 28. And I can see arrows at the top, so it keeps going left and right. So if I'm working on these, I normally can't look at them on a computer. I need to print out all the pages and tape them together. And you'll see here where this wire goes up and it may go across to other things. It tells me here, this is J285. So I need to come down here to my decoder, and J285 is my control module with indicator unit for instrument panel insert. Okay, so that tells me what that is. So this thing here, nothing is named. Everything has little acronyms next to it. And I have to use the decoder at the bottom of each page. A lot of people get very confused using these on European vehicles. So they like to use Mitchell or aftermarket schematics where everything's drawn like they're used to seeing on a domestic vehicle. The problem is they normally make tons of mistakes when they do that, and the schematics are not accurate. So if I'm diagnosing a European vehicle, I'm actually going to want to use these track wiring diagrams, which means I'm going to need to learn how to use track wiring diagrams. If I work only on Asian or domestic vehicles, I can completely ignore this other than knowing they exist, because I'm never going to see them working on an Asian vehicle or a domestic vehicle. These are exclusive to European vehicles, but I did want to show them to you so you know, A, what I mean by track wiring, and B, if you ever open a book or you see this, you're not going, whoa, this is completely different. What is this? Mr. Brian never talked about this. No, I did. Here it is. This is what they are. And they're really not bad, but the trick is knowing you got to print them all out. What we used to do is print them out, tape them all together, and we lay them from the trunk all the way up the back window across the roof of the car and get the highlighter out and start highlighting what we're working on. And that worked really well. But trying to do it off 1 or 2 pages or make a book and flip pages, you're going to get really turned around. This right here is DIN circuit numbering. So one of the questions that came up yesterday was, is there any rhyme or reason circuit numbering? And I said on domestics, there's not. On European vehicles, and this is just part of DIN, this isn't the whole thing. I just put 1 page in here. You can see there is some standardization. So down to the glow plug switch or electric motors, starters, relays. They also have some standardization on their colors with DIN. So unlike domestics that tend to kind of be all over the place with the colors, European vehicles are very, very precise on what you can do with what color wire. So DIN is what that is. There's this, I probably pulled this out of a 20-page document talking about DIN and DIN numbering and wire colors and circuits. I don't expect you to know these. The only one you might learn being in this class is circuit 30, which is battery power basically all the time. See circuit 15 is switched battery power. Really don't talk about that much, but we'll see when we look at relays, they have a terminal 30. All the other terminals are relay are 85, 86, 87, and they're not on the sheet. But that's standard on a Bosch relay, which is used worldwide by every manufacturer. And that's the only reason why I know those numbers is because they're used by everybody. And since everybody uses a relay, it makes diagnosis easier. And we'll look at that when we look at relays. But the numbers that you see on the relays, when we learn about relays, are that DIN numbering, because Bosch is who invented it, and they're based in Europe and use DIN. So here on the electrical schematics, find each of these basic circuit parts when reading schematics. So one of the questions came up is, hey, what do I really expect to be able to know? I'm not going to go do this for a living. I don't want to be an electrician, but what should I get out of this? So these next couple of slides really show what we should be able to identify. And I'm doing it by color. So identify the circuit. So if I want to identify the circuit, well, that's what? The number next to the wire, isn't it? And so here is my load. And there's
no PowerPoint, Mr. O'Brien.
Oh, there's not. Why is that?
I can see it.
Okay, good, because I have everything turned on.
You are on iPad and you have a different situation. Also, you are not muted many times, so.
Okay, it can also be how your display, you got some little dots in the upper left. So you may have where you're just seeing me and not showing my share screen, which happens sometimes. So we can see the power source and the ground source.
No, Mr. O'Brien.
What's that?
No.
No?
See it.
So we can see here, I have a complete circuit, don't I?
Yes.
I have my power supply, my conductors, and a load. So even though this looks confusing, I have a complete circuit and I've identified each of the components. So this is the key thing we need to be able to do. Just like if I'm looking at a map, I needed to figure out what's a roadway and what's a river, right? Otherwise, that might be bad. Now, of course, if I'm in Fairbanks in December, the river is the roadway because it's all frozen. But we're not in Fairbanks, so we probably don't want to drive in the middle of the river. And this is what's called a ground switch circuit, because the switch that controls current flow is on the ground. So if you see here, part of the circuit has power all the time. The ground only gets ground when the switch is closed. So therefore, it's a ground controlled or low side controlled circuit. And this is an actuator circuit. So here's another component, a solenoid. We have our power supply, our ground source, and it's a ground switch circuit. So really, electrically, as far as from a diagram, the check engine light, which is a light bulb, is the same as our solenoid, which is uses electromagnetism, isn't it? It's the same circuit, isn't it? Isn't it a series circuit that's controlled on the ground? The only difference is the load. Everyone see that?
Yes.
Right? Because it's the same. And that's why I use light bulbs in so many examples, because it really, how the circuit works, it doesn't change. Now the amount of current flow or what we're doing changes, but the actual build of the circuit, the framework, doesn't change. So now if I look at another, so when we look here at DC electrical circuits, there's 8 different kinds of faults we can get. I can get an open on the power side or ground side. I can get high resistance on the power side or low resistance on the power side. high resistance on the ground side or low resistance on the ground side, a short to power or short to ground. So electrically, those are the faults we can get. Now, of these 8 faults, there's only 4 faults we're going to diagnose. We're going to diagnose an open circuit, a short circuit, because we know because of Ohm's law and a series circuit, if I have an open anywhere, the circuit doesn't work. So the fault's the same, whether it's on the power or the ground. The location of the fault changes, but the actual fault is still an open circuit. Just like if I have a short, I could have a short to power, or I could have a short to ground. If I'm shorted to ground, I'm probably going to blow a fuse. If I'm shorted to power, my light bulb might not ever turn off.
So there's 2 kinds of short, Mr. Brian.
Yes, I can be shorted to power or I can be shorted to ground.
Oh, you can do short to the ground. It's already in the ground.
Right. So, for example, if my ground wire is shorted to ground, no one's going to diagnose that because that would be what? Low resistance to ground. Who cares? I have an extra ground. But if that ground is shorted to power, now what? We're blowing a fuse. We're melting things. That's a problem. If my power side, if I have a power side switch system, and that power side is shorted to power, maybe it acts like a bad switch because it's got power to the load all the time.
You mean to say short to power, we have a fuse that get busted, but short to ground, nothing will be busted except going to the ground.
Oh no, a short to ground will blow a fuse because if the circuit is shorted to ground before, I'll back up. So if I am shorted to ground right where this arrow is, this fuse will blow because I have power and I go to ground with no load, right? With no load, there's no restriction. We're going to blow a fuse.
Okay.
Right.
So that's why it says short to ground.
Right. Exactly. Because
How about short to power?
Well, hold on just a second. If circuit 428 is shorted to ground, I'm not going to blow a fuse, but the solenoid would stay on all the time, wouldn't it?
Yes.
Right. Because so it's the same short, but 2 different symptoms. So if I'm shorted to power and I'm shorted to power on the power side right here, it's not going to make a difference. If I'm shorted to ground here, whatever circuit is shorted would blow a fuse because then it's a short to ground for that circuit. But what we have happen is some circuits have put the switch on the power side. So I might have a short to power between the switch and the load, keeping the load on all the time. And it acts like a bad switch. It's like the light bulb won't go out even though I turn the switch on and off. I put another switch in and it still won't go off. Well, it's because it's getting power from somewhere else because it's shorted to power.
If you had a short to ground, wouldn't it like not supply the load? Also, could it not supply the load? It would take the shortest path of resistance.
Right, exactly. That's why it blows the fuse.
You mean to say, Mr. Brian, if you have short to ground, all the load is like going up and breaking the fuse because there's no load.
Right, there's no load. So you blow the fuse, the load wouldn't work.
Current.
Right, all the current's going to go through the short because that's this. Actually, it won't all go through. You know that from parallel circuits. If this was energized, some current would still flow through this and the rest would go because it's just what creates a parallel circuit to ground. But so we really only have opens, high resistance, short to power, short to ground. Those are the only 4 things we ever diagnose on a DC circuit. So an open circuit, high resistance in the circuit, short to power, or short to ground. Those are the only 4 of these where we're going to diagnose, because high resistance, again, because we know current flows the same everywhere in the circuit, it doesn't matter whether it's on the power side or the ground side, we're going to diagnose it the same way. If I have an open, it doesn't matter if it's on the power or ground side, we're going to diagnose it the same way. The only thing we diagnose differently is if it's a short to power or short to ground, because it's going to have different symptoms and we're going to diagnose it slightly different. But when you think about that, all the circuits we have on the car, all the components on the car, a new car can have over 160 computers on it. And yet there's only 4 different electrical faults we'll ever need to diagnose. So doesn't it make sense to think about how things fault and how to diagnose those faults? And then if I read a wiring schematic, look at how the circuit's built, figure out what volts I should have at a particular test point, go use my tools to test for that. And based on those results, I can decide which of those 4 faults I have and then diagnose it. So it really tends to compartmentalize things and make it, because I see stuff all the time I've never seen before. So I have my contractor is here, who's a friend of mine, and his 58 pickup truck wasn't running, his fuel pump wasn't turning on. He has an aftermarket fuel injection system on it. Don't have any manual, never seen it before. I go over there and in less than 10 minutes, I figured out how the circuit, with no schematic, I figured out how the circuit works and what's wrong. And he has a bad driver inside his computer. But I was able to figure it out very quickly because I know how circuits have to work. I know a fuel pump needs power and ground. Where is it coming from? Well, ground was right next to it. Power is coming from the computer. Well, let's see if the computer is giving it power. From there, I checked, is the computer getting power? Well, the computer's getting power, but not giving power. I'm going with it's a problem. And actually, I was able to test it. It's got a bad transistor in it. And that's what I mean by I never replace a computer or repair a computer unless I know exactly what's wrong inside. But by understanding electricity, I remember a couple years ago, I had a student and she told me one morning, we're out in the lab, and she goes, you know, I had a dream last night. She goes, I finally got schematics. I was dreaming and I dreamed how the light in my refrigerator works. And I dreamed the whole schematic, and I know how that circuit has to work. Because it has to have power, ground, it has to have a switch, and the switch is there and it makes the light come on. And I mean, she was just able to visualize it. You know, that's power. Because I don't teach refrigeration. I'm not teaching how your refrigerator works. But what is a series circuit with a load? It's got a switch, a light bulb, and power and ground, right? What's the difference? And to me, that's really empowering. So let's see how we're doing here. So I have a vehicle, this vehicle right here, and it has a problem. The high beams don't work. The low beams work fine. And the high beam indicator works fine. So I'll say it again. My high beams don't work. My low beams do work, but my high beam indicator works normally. So let's look at this for a second, and then we'll walk through this. Because everyone in the class now can fix this. You don't know it yet, but you can.
I think there's a ground.
Well, we're not going to think. We're going to walk through and be methodical, because I don't go to Vegas because I'm not lucky. So let's walk through, because a ground's a possibility, but let's see if we can figure out if it really is a possibility by looking at the schematic. So if I start at the top, could it be a bad circuit breaker?
No, because the
Oh.
indicator.
Because the low beams work, right? And they
That's
get
right.
power from the same place. Could it be a bad headlight switch?
No.
Maybe.
No.
No, because what? High and low beam both get power from the headlight switch, and low beam works fine. Could it be my dimmer switch?
No.
No, because the high beam indicator works and the low beams work. So it can't be the dimmer switch. So to right here, we know we're getting power, don't we? So someone brought up a ground. It could be a bad ground, but wait a minute. Aren't these two different grounds, G108 and G109? And don't we use the same ground for both the low beam and the high beam? So it really can't be a ground, can it? So the problem has to be either we have two bad light bulbs, or there's a problem somewhere between this splice and the light bulb. So it could be at our bulkhead connector right here, and it tells me which pin it is, 9D. Maybe I have a melted pin or something in the connector. Maybe I have two bad light bulbs. So now it's what's easiest to get to? Well, if it's the light bulbs, I'm going to go there, aren't I? Because I can test for power very quickly and or put another bulb in or something like that. But you see how we fixed what's wrong. We figured out what can't be bad through process of elimination, which left us with very few things that could be bad. Did everyone follow the thought process there? Would you like me to go through it again?
Mr. Brian,
Yes.
the dark line is the one I have a load going to the high beam, right?
Yeah, the black wire is the high beam, the tan wire is the low beam.
So your question is why we don't have a low beam?
No, why we don't have high beam.
High beam, okay.
So my low beam lights work and my high beam indicator works, but my high beam lights don't work. So it can't be the circuit breaker because it powers both the high and the low beam. It can't be the light switch because it powers the high and the low beam, and the low beam works fine. It can't be the dimmer switch because low beam headlights work and the high beam indicator light works. So I know I'm good up to this splice. And it can't be a ground because it's two different grounds and the ground is shared by both the high beam and the low beam, which means my problem has to be either the light bulbs or the wiring here coming up, maybe inside this connector up to this splice. So then I just have to decide what's the easiest place to get to test. You know, some cars today, it's 2 hours to get to a headlight bulb. Well, now the bulkhead connector might be the easiest place, right? But if it's 5 minutes to take a headlight bulb out, then that's the easiest place. So there's not a right or wrong. The idea behind this is instead of going, it might be a ground, it might be a dimmer switch, it might be a headlight switch. You're right, it might be, but we want to look at a schematic and see what we can prove isn't the problem. Then we can narrow down to where the problem has to be, and that's where we go test. Does that
I
make
think
sense?
the high beam filament is not working. There's a two filament, high and then low.
Right. So the high beam filaments aren't working. Are they not working because the filaments are bad? Or are they not working because the pin at the bulkhead connector is bad? Or are they not working because a rat chewed through the wire right here? We have a lot of rats in Fallbrook. So I don't know what I'm going to find, but what I did do is I quickly figured out what area the problem has to be in. Now it's just a matter of what's the easiest place to start testing.
Mr. Brian, before
Yeah.
you go on, a dummy question. What exactly is the ground? When you say it's not the ground, what does that mean?
Okay. So in our circuit, we have the positive and the negative side of the circuit, correct?
Yes.
Okay. So the ground is my negative side of the circuit. So when I say it's not the ground, what I'm looking at is I'm looking at my G numbers. See G108 and G109?
Yes.
Those are two different grounds. Okay. And then the G109 comes over and it is attached to both my high beam and my low beam, meaning that both the high beam and the low beam use the same ground. So it doesn't make sense that the ground would be good for the low beam, but not the high beam, especially on both sides when it's two different grounds.
I still don't understand what you're explaining. I'm not getting the ground thing connected to all these. Is it only me? Sorry.
No, I'm sure it's not. And that's why I'm trying to. So the ground, right? Because the ground, this ground symbol goes all the way back to my battery. Right? So here's my ground symbol, and here's the wiring that comes over and attaches to both my headlight bulbs. So I have the power that comes down, and then it goes through my load and over the ground. So and if I go on the high beam side, I come down through here, through the light bulb to ground. So they both share the same ground connection. So in this case, it's next to the radiator. So even though my circuit goes all the way back to the battery, I have a connection where this ground wire is bolted to the side of the body next to the radiator. And what I'm saying is I know that connection is good because the low beam works.
Oh, okay. So you're
Right.
saying the connection of that ground to wherever it is connected is okay.
Right.
Oh, okay.
Yep. No, and that's why I want to be clear, because I'm sure that if you're not clear, then someone else isn't clear. And one of the issues I have, and you all need to slow me down sometimes, is because I teach at a lot of different levels, sometimes I use something or I'll say a slang and people are like, what the heck is he talking about? You need to kind of back me up and have me explain it, because I'm going to use that term for the next, remainder of the class. So if we're not getting a term I use or an acronym I use, please stop me and ask me to clarify it and explain it. So we're talking the same language.
That's why, Mr. Brian, I want to clarify. You said that there's no power going, the high beam doesn't work because there's no power, right? It's grounded.
Well, no, I said the high beam doesn't work because it's either the bulb itself is bad or it's not getting power to it. Correct.
But the ground is working, right? It's going back.
But the ground is working.
Okay, right.
Yeah,
That's
and
why
we
I
can,
try to elaborate in the classroom so they understand. Some of them are like, oh yeah, but they don't understand.
no, I know. And this is a big jump because we're dealing with basic circuits. You've seen schematic, and now I just asked you to help me diagnose a car. Right? So this was a big jump. But one of the issues I have with traditional automotive education is that the book tells you about everything and it says, here's all these neat little pieces. And you've gone through and spent a year in school and you're looking at your first broken car and you have no idea where to start to figure out what's wrong. You know how all the pieces work. You've been to school on it, but how do I figure out why it's not working? And it's like a flat line on an EKG. We have no idea because that's not part of the traditional curriculum. And yet it's the first thing we have to do when we're working on a car, isn't it? Because you're not going to take apart your headlights and look at them when they're working. You're going to look at your headlights when they're not working. And, odds are it's a bulb. It almost always is. But what do you do when you put a light bulb in and it still doesn't work? Well, then you need to what? Have a backup plan.
Mr. Brian, I have the experience with that. The technician says my filament is not working. And we check the continuity. There's no continuity of a electric circuit going to the bulb. That's why
Right.
they said the filament it's not working. So I changed the bulb. It's worked.
Yeah. Well, exactly. And that can happen. But like I said, the whole purpose of this was to kind of tie the wiring schematic idea into how can we figure out what's not wrong before we go work on the car. Because I see people a lot of times, they've bought a lot of parts and their car still doesn't work. Because they're what? Well, maybe it's this, maybe it's this, maybe it's this. Well, maybe I'm going to win the lottery, but probably not since I don't buy a ticket. Maybe I'm going to live to be 100, probably not the way I eat. So there's a lot of maybes out there. But let's figure out what we can prove isn't wrong, because that narrows it down. And they call that testing by exclusion, right? We do that in science. We do that in a lot of different professions. Let's prove what it can't be, which means what? Now I'm what? Looking in a much smaller haystack for my needle.
Mr. Brian,
Yeah.
so there's only on the right side, ground on the right side, there's only one ground for both high and low beam, correct?
Correct. And then same on the left side, and it's a different ground.
Yeah, got it. So see that.
So the ground is pretty much going to be connected to the body, and the G01 and G09 and G201 is just the spot where, which part of the car is that, ground connected to the body of the car.
Exactly. And the fact that it's two different grounds at two different places and both light bulbs aren't working, what are the odds it's a ground? Pretty small. Plus the low beam lights are working, which pretty well means it's not a ground. So I don't even need to go find it or test it. And one of the things I don't like about traditional electrical education is if you look at the troubleshooting, the book talks about this, always says, we'll start testing at the fuse. It's always, we'll start at the fuse, test the fuse first. Why would I go test the fuse here? Or in this case, a circuit breaker. I've already proved it's working. The low beam headlights come on. And then the book says, well, go test the switch. Okay, great. Why would I test the switch? I've already proved it's working. So if I can prove it's working, I don't need to go take it apart and test it. So the thought process is still there that the book's talking about, but the physical effort, I've spent 20 minutes before just trying to find a fuse. Because there might be 3 or 4 fuse boxes on a car. They might not be labeled well. I've wasted a lot of time just looking for a fuse. I don't want to go find a fuse if I don't have to.
Yeah, that makes sense. Yes.
Yeah. So, that is, And again, a lot of what I teach, I try to bring back to the real world of why is it important? How would it help me? Or how could I use it? And that is there. So this is an aftermarket schematic. This is the same car, but a factory schematic. Looks a little more confusing, doesn't it? I mean, it's lower resolution. But if you notice, I've got a connector number here, a splice number here, a grommet number here. It tells me to see ground distribution, meaning these two grounds are used for a lot of other things. So if I had a background, I'd have more than just headlights that aren't working. So there's useful information. And if I back up one, you'll see what I'm talking about. So right here, it shows me there's a connector, but no number. Well, without a number, how am I going to know what pin does what? Here I can see there's a splice, but there's no number. So how would I ever find the splice? I don't know. Here there's a bulkhead connector, but again, no number. And then I don't know when I'm going through metal. And here it clearly shows, here's my bulkhead and gives me a connector number. And then it shows me with grommets when I'm going through the front of the car up to where the headlights are. So it can really help me. Again, where's this splice? Well, it's obviously up by the headlights. It's not back under the hood. So it can, where this splice here is what? Under the hood, not where the headlights are. So it can help me locate things. So although these can be more confusing, they're more confusing because they give us more detail. So sometimes people will use the aftermarket schematic to kind of do what we did and then go, okay, I need to know this number, or I need to know this number. Now I'm going to go into the factory schematic. I know what I'm looking for and get the number. So, you know, the reality is people tend to use both. I use almost all factory schematics because they have the detail level that I need to diagnose the car. But sometimes I'm not getting the relationship that I want, or I'm not getting the big picture. So I'll look at an aftermarket schematic to kind of see what I'm looking at, and then go over to the specific factory schematics to get the detail. So, you know, one is not necessarily better than the other. They're different. And, you know, you need to understand. The other thing is you'll see errors in an aftermarket schematic like this that you won't necessarily see on the factory schematic, because these are drawn based on the factory schematic. And since we have another set of hands in there, it's a chance to make mistakes, because we all make mistakes. So I've had things reversed. I've had wrong colors. I've had a lot of stuff wrong on aftermarket schematics that have hindered me fixing a car. Years ago, I had a BMW I spent a couple of days on using an aftermarket schematic. I finally went over to a friend of mine's shop and pulled up the factory schematic. It took me 10 minutes to figure out what's wrong once I had the factory schematic. The aftermarket schematic was completely wrong. So, you know, it's important to understand when things don't make sense. Hey, wait a minute, it might be the source I'm using. Also, these aftermarket schematics are made with what's called pre-production diagrams. In other words, we expect to make the car this way. So we expect to use a green wire with a red stripe. But you know what? They were out of that. And so instead we used an orange wire with a yellow stripe. So if I'm using an aftermarket schematic and I'm looking for that green wire, I'm never going to find it because it was never built that way. The factory diagrams are updated after they build the cars. So a lot of times you'll see a wiring color difference with aftermarket schematics. Not all the time, but it's definitely not uncommon, and that's why that happens.
Question about the, how do you get your hands on a factory schematic? I've seen the aftermarkets with the Pro Mitchell and all that, all data.
Well, all data uses factory schematics, although all data is starting to give you a choice of either the OE or the aftermarket. Mitchell is all aftermarket.
Okay, thanks.
So I like all data personally. And I mean, I've, you know, tons of Mitchell books. I used Mitchell forever. Their online stuff is just not as good as the all data stuff is. And it's two different things. Mitchell does a good job of, let me hold your hand and we'll walk through these steps to try to solve this code. But they won't tell you what the computer saw to set the code. All data tends to, here's what the computer saw, here's what made it unhappy, here's the schematic, go figure it out. So I like that because I want to know what made the computer unhappy so I can fix it. What I hate is going through a diagnostic chart where I'm on step 3 with a meter wanting to know if it's above or below 11 volts, and I have no idea why I'm doing it or what I'm trying to figure out. Or I get to the bottom and it says replace with known good unit. Well, that might work fine at a dealership when I have another car to take a part off of. It doesn't work so good when I'm working aftermarket and that part's $500. And I tell the customer, well, I don't know what's wrong, but the book says to put a new one in and we'll see what happens. It's only $500 plus labor. Right? So I want that additional information. That's why I use ALLDATA, because ALLDATA is going to say, you know what? It set that code because the voltage on this circuit was over 12 volts when it should have been under half a volt. Boom. Now I know what I'm looking for. Let me go test it. Or I could go through this long step, and an example would be Honda for a throttle position sensor. The first thing you do is disconnecting the wire at the sensor and at the computer and checking all the wires. Step 23 has you actually test the sensor. Guess what part goes bad the most? The sensor. Wouldn't it make sense for me to go test the sensor first? And if I'm not getting good voltage to the sensor, I know where to go. If I'm getting a good voltage from the sensor, but not to the computer, hey, it must be the wire between the computer and the sensor or back computer. Wouldn't it make sense to check at the thing that's the easiest to get to and goes bad the most first? But the engineer put that at step 23. And that's why I don't like flowcharts. I'd rather know how the circuit works. Let me know what the computer saw, and then let's come up with a test plan. And we can only do that by understanding wiring schematics and electricity. And that's why I teach the class the way I do. And let me tell you, it gets a lot easier that way, and you fix a lot more cars. So I'm going to stop my screen for a second. I'm going to change presentations.
Mr. Brian, I was just going to ask you about flow charting, because the schematic drawing that you have, sort of like when you went through it, you're answering yes and no questions,
Right.
and you're flowing. It's kind of like a flow chart, isn't it? And you said you don't like flow charts.
Correct. Except for the difference with a flow chart is going to tell me step 1, go measure, verify that there's voltage at both sides of the fuse. Step 2 is going to be check for the voltage at the wire going to the headlamp switch. Check for voltage coming out of the headlight switch. So it doesn't allow me to use common sense, which we did. It wants me to go do those specific steps, or it may be, instead of measuring voltage, it may be disconnect the wire at both sides and use an ohm meter, which is not terribly accurate. So, flow chart, if I'm working on something I've never worked on before, I may look at a flow chart to kind of see where they're going with their diagnostic process. But again, flow charts, you see this a lot with Toyota. Depending on the code, the flow chart may be 4 steps or it may be 4 pages. And I think it depends on which engineer wrote the flow chart for that. So what I see a lot with flow charts is that people are doing tests based on what they're asked to do, and they don't know why they're doing it. And if you don't know why you're doing it, you probably shouldn't be doing the test. And that's probably my big beef. And I guess also because in the early days, all we had was flow charts and books, because they weren't sharing and we really didn't understand. And we didn't do a good job of fixing customers' cars back in the 80s using flow charts and into the early 90s. So I think that's where a lot of my, discussion of I think that's why I don't like them, is I've seen how many cars aren't fixed by them. And even by the manufacturer's own numbers, if you follow the flow chart and follow factory procedures, you're going to fix 80% of the cars.
But wouldn't it be helpful for somebody who's not as knowledgeable as you, for someone who's just trying to learn some things?
Yes, absolutely. It could be helpful. Absolutely.
I think the flow chart from the manufacturers, they limit people to know exactly what happened, when it comes to like you doing diagnostic, because they just say, just replace the part, but they don't explain why.
Right. And for what we just talked about, which is the headlights, there is no flow chart for it. So there's normally flow charts for computer codes. So if my computer has a code, there's normally a flow chart. But most things that don't work, whether it's the window not going up and down or the headlights not working, there is no flow chart.
Would you not minding checking your chat, please?
I have the chat up.
Hey, Brian, I don't want to interrupt you, but there was a question on the chat. Once you determine the computer, the transistor is bad in the computer, can you just replace the transistor?
Yes, that you can. I don't. Normally I'll send it out to a computer rebuilder and have it done, but yes, it can be done. We don't normally do that in industry because I got to warranty it for 2 years. But yes, you can do that. And then the big question is, why did the transistor go bad? And normally the reason why a transistor goes bad is you're flowing too much current through it. So it's usually a problem with the load. The load has too low a resistance, so therefore too much current flows through it. So if you replace a transistor in a computer, you need to make sure you check the circuit that transistor is turning on and off, because it will, that's usually why the transistor went bad. And if you don't fix the circuit, the new one you put in would just go bad.
How would you usually fix those if they do burn out the board? Exactly.
Exactly. What I do is I either send it to a computer rebuilder, I put a used one in, or I put a new one in.
Yeah, what if I can't find a good used one for those?
Then you're looking at a rebuilt one or a new one.
Yeah, the rebuilt ones is pretty much burnt boards, but I haven't been able to find anyone to repair it. I have the board, but it's not. I haven't found a shop to be able to repair them.
Yeah, a shop's not going to. There's one guy back on the East Coast that repairs the Mercedes ones. I think it's Beckman, I think is the name of the company. I know it starts with a B. I could be a little bit off, but he's back on the East Coast. He does all the European different computers and modules. He's in instrument clusters. He's the only guy that does them, can unlock them, set them so they can be programmed again. That's the guy that does them. And if he doesn't have one or won't do it, you probably won't find someone who will.
Yeah, pretty much. I wasn't able to find anyone that was able to repair those. They just said to replace it most of the time. The boards is completely burnt out.
Yeah.
They can't solder or anything.
Right.
So, Mr. Brian, you mentioned that because the transistor within the computer failed, there usually is another problem that caused the excess current flow.
Correct.
Is that problem inside the computer or outside of it?
Outside.
So a replacement of a full assembly of the computer may bring us to the same problem again, and another transistor will burn out.
Right. That's why you have to diagnose the circuit that transistor controls.
Wow. How many shops would do that?
Maybe half. Other ones just put one in and don't understand why the new computer went bad in 3 months or 6 months.
Okay.
So then, of course, especially if they're putting in rebuilt computers for something like Napa, then it's, well, the part's defective. The part's defective. And that doesn't even pass the smell test. Let's think about it. What are the odds that you have two computers with the exact same failure? I mean, the odds are astronomical against that happening. So, it kind of brings you back to, hello, you missed something. You know what I mean?
Yes, this is really a thinking point here. So how would you even find that failure, the actual cause?
Okay, so the most common thing we see is fuel injectors. So what we would do, the first thing we do is we check the resistance of the injector, because the load, you remember the load is what controls the current flow through the circuit. So if the transistor is blown, either I have a short, right? A short to ground somewhere, bypassing the load or in addition to the load, or I have a load that has low resistance. So for example, an injector that should have 12 ohms of resistance, if it only has 3 ohms of resistance, that's what? 4 times the current flow. That's going to burn up that transistor.
Thank you for the explanation.
You bet. So I'm going to jump into electrical testing here. We went a little in the weeds, and that's okay. But no, in industry, we really don't open up and rebuild. You know, I've replaced quite a few rear SAMs. When they're bad, we put a new one in. This is how much it is. So there's things you can do at home that I would never do in the shop. There's things I could do at home that I'd never do in the shop because it's not a reliable repair or it doesn't meet acceptable trade standards. Does that mean that you can't do it on your own stuff and potentially get away with it or have it work? No, I'm not saying that. I'm just saying that if you got to stand behind it for 2 years and you're charging the customer money, it's not what you're going to do. So that is the, you know, so kind of a little different perspective. So, you know, kind of like when you ask me, what would I do? I'd be putting a new one in. Here's how much it is. My car runs fine, right? It's different when it's not your car, right? So electrical testing, test points and tools. So we're going to go through here. We're going to talk about test points, and we're not going to come close to finishing this today. We're going to talk about test points. And at the end, I've got some different tools that we use that I'm going to talk about. So really about electrical testing and, you know, about application. So you're going to hear me use the term test point voltage, what the voltage should be based on Ohm's law at any point in the circuit, right? Because I got this cool tool, I'm going to hook it up and it's going to give me a number, but how do I know that number is the number I should have? So in this example, I have a simple series circuit. It's high side controlled or power side controlled. So the switch, that means the switch is on the positive side. And I can see here I have a 12-volt battery and I have a motor that I'd like to go round and round. So the trick is, what should my test point voltage be? So if I look here, my test point voltage between here and ground should be 12 volts. Between here and ground would be 0 volts. And between test point 3 and ground should be 0 volts. Now that's with my switch open. But if I close my switch, things might change. So the goal here is to understand what test point voltage should be. And this is the basis for electrical troubleshooting. So this is what takes us from looking at that schematic to actually understanding what the voltage should be at each point in the schematic, which helps us with some of our other exercises. So here the fan motor circuit has an on-off switch is in the off position. And if I measure the voltage difference between the two sides of the switch, I would see 12 volts. There's no current flow in the circuit, but voltage pressure is available at the power side of the switch and the ground side of the switch, because I can't use my ground in my motor because there's no current flow, right? So I'm going to be electrically the same all the way from the negative post of the battery all the way to the tip of the switch. I'm going to be electrically the same from the positive point of the battery all the way to the tip of the switch. When I measure across the two sides, I'm going to see the same 12 volts I see at the battery. Now observe what happens to the test points when the on-off switch is placed in the on position. Hey, my motor goes roundy round. It must work. So test point 1 is going to stay the same at 12 volts. Test point 2 is now 12 volts. And test point 3 remains the same. So you can see here that my power supply should never change, my test point 1. My ground should never change, that's test point 3. But my switched power, which is where test point 2 is going to change based on the condition of the circuit, whether the switch is open or closed. And this is what gets people confused. So sometimes someone will check test point 2 and the circuit's open and they see ground there and they think they have a shorted switch. They may go to test point 3 with the switch closed and they see 12 volts there. And the motor doesn't work and they think the motor's shorted. No, if I have 12 volts at test point 3, that means what? I have to have an open or high resistance between test point 3 and ground, because we know ground is 0 volts. So the only way test point 3 can have voltage is if there's resistance between test point 3 and ground. Because we start with our 12 volts, we use it all in our load. I only have one load. Ohm's law says I have to use all of it. and then we come down to ground. Now, when I measure across the switch, I see 0 volts because my switch is now a conductor and both points are electrically the same. So my voltage drop across the switch is now 0 because the motor is using all the available voltage. Does this help a little bit walking through this?
Yes.
Kind of visualize it a little bit, give you a little fan to go around, keep you cool.
Yeah.
I don't want anyone having a heart attack because they're too hot. So I got the fan. So this is what people struggle with. Where, and again, I've got a motor here, so we stay cool, but this could be a solenoid, this could be a light bulb, it could be anything. It doesn't matter. What we just talked about is going to work the same way. So now current is flowing because the circuit is complete with the switch closed. So now we're going to work on these lab sheets. So I sent these out to you. So if you did print them, go ahead and pull it out. And if you didn't print it, that's okay, because we're going to do this together. So my first question is, what would my amp meter read right here?
Volts.
No, volts
Amp.
is up here, right?
The
Amps.
3 amps.
3 amps, right? Because I got 12 volts, 4 ohms would have to be 3 amps.
3. Mhm.
So what is the current flow of the circuit? It'd be 3 amps. Okay. So what I did with these is we're going to kind of build, we're going to build a series circuit and build on it. And then we're going to look at a parallel circuit. And then we're going to look at a series parallel circuit. So is current flow the same throughout the circuit?
Yes.
Okay, we know that, right? So now taking it to the next level, what is the voltage reading on DVOM number 1?
12.
12 volts, right? Because I haven't used any of my voltage. I'm before the load. What is the voltage reading on the voltometer number 2?
12.
Should be
because
0.
my load uses all.
0 volt. 0. Yes.
It wouldn't be 0. You had it right first at 12. Let me get this to click.
Oh.
And what is the current flow? So if I come in here, here's the current flow. Oh, I see my timing's out. Doggone it.
Get it, Mr. Brian.
Oh, you're right. DVO number 2 is 0. I was looking at 3. You guys are right. I'm wrong.
You get that,
Sorry
Mr.
about
Brian?
that.
I'm late.
What's that?
I don't get it. You said you're 12 volts, right?
No, I just said I was wrong. I was thinking number 3 was number 2.
Oh, in the beginning it says 12 volts and you got DVOM for 12. How you get that? Because I was in the restroom.
Oh, I'm sorry. So I have battery voltage. I'm before my load in a complete circuit. So I have to have 12 volts here. My
You
DVO
divide
number
4
2.
to 12.
What's that?
The volts goes to the DVOM is 12. That's why you said.
Right, because I'm measuring the difference between the voltage on this wire and ground. So since I started with 12 volts and I haven't used any of it, I should have all my 12 volts. So DVOM number 2 is at ground, comes up, and I should be near 0 volts because the difference between this wire and ground should be 0.
Okay, there's the 2 ground in between the, what's that, DVO2. DVOM2 is 0, right? That's why.
Right, right, because I'm measuring the difference between ground and this wire is attached to ground right here. So they should be the same, shouldn't they?
Yeah, because there's 2 ground and
Right.
there's nothing.
There's no difference.
There's no going. It's only ground. There's 2 ground.
Right. So my meter just tells me the difference. So my meter is saying, hey, there's no difference between ground and what's in this wire. Then the question was, what is the amp meter read? What's the current flow? Well, 3 amps, because we already figured that out on the last slide.
You get
And
the
now the
three.
question is, what does DVOM number 3 read?
Hold on, Mr. Brian. How do you get 3 amps? You divide 4 to 12?
Yeah, you
Yes.
take 12 volts, 12 volts, divide 4 ohms, and that's going to give me 3 amps because 3 times 4 equals 12.
Following now.
Okay, good. So now for the hard question, what's DVOM number 3 going to read?
12.
12, because we know that my load has to use all the applied voltage. Does a light bulb use all the voltage available in the circuit?
Yes.
Yeah, absolutely. If it doesn't, we have a problem with the circuit. So that's why a
Give us
lot
another
of
sample,
times,
Mr. Brian.
what's that?
Everybody now is learning, so give us another sample.
So that is why a lot of times when we're testing something, we just take the voltmeter and test the voltage across the load. Because if I went across the load and only had 9 volts, I instantly know I have a problem somewhere else in the circuit. So that's why that's such an important concept. So now, how many watts does the light bulb consume?
Well,
Now we're talking about the Watts formula.
The Watts formula, right? Which is what? Volts times amps equals watts. So how many watts are we going to use?
I have a copy, but I have looked.
Oh, no, amps. The 3.
Watts.
What? 6.
Right? 36. Yep. 12 volts times 3 amps, 36 watts. You
Does
wanna
this
correct
mean
me,
that, so this light bulb has a printed 36 watts on it? Does this mean it?
Yeah.
So 12 volts times 3.
Yep. Gives me the wattage, 36 watts.
Yeah, you're right. It's 36 volts times amps.
Yep.
P times A.
Okay. Now, let's look at this series circuit. Now I've got 3 resistors. Oh no, Brian made it hard. So let's take a look here. So let's ask a few questions, okay? What is the applied voltage to this circuit?
12 volts.
12 volts,
12
okay?
volts.
Again, I just want to get us all on the same page. And so I don't jump, and start throwing things out there and you're wondering where I get it from. What is the total circuit resistance?
3. 4.
4 ohms, right? 1 plus 2 plus 1 is 4, at least when I went to school. So 4 ohms.
That's a series circuit, Mr. Brian.
Right? It's a series circuit. So I got total resistance is 4 ohms. Now, what is the current reading at amp meter number 1? How many amps are we flowing?
3.
3. What is the current reading at amp meter number 2?
Should also be 3 if it's a
3
series.
amps.
Right, it has to be, doesn't it? Because that's one of our rules. So I got 3 amps everywhere in the circuit. So now what we need to do is, what is the voltage reading at DVOM number 1?
12.
Well, if it's 12, what do the other guys get to eat?
0.
Well, they
It's
can't
3.
have 0. We can't starve them. We got to spread it out.
Is it 3?
No, it gets distributed. Yeah.
3.
Right, because we take our current flow, our amps, times our resistance, comes up with 3 volts.
3. Mhm.
So what is the voltage reading at DVOM number 2?
6.
And how about number 3?
3.
There you go. So you could see where we started with 12 volts, we used 3, then we used 6, then we used 3. So did my loads use all my voltage?
Yes.
Yes.
Now is the applied voltage is equal to the sum of the voltage drops. So now let's take what we just did and measure our different test points to ground. So continuing from what we learned on the last slide, what is the available voltage each of the test points shown? So what is DVOM number 4 going to read?
12.
12, because we haven't used anything, right? How about DVOM number 5?
9.
9, because we used 3 volts, right? I had 12 volts. I just used 3 volts. I have 9 left. How about DVOM number 6?
3.
3.
3, because I had 9 volts. I'm going to use 6 volts. I got 3 volts left. And now what is DVOM number 7?
0.
Oh, so kind of like balancing a checkbook, right? We start with our money, we pay a couple bills, and we end up with 0. Same thing.
Hey, Ryan. So it's pretty much the same reading that we get at the battery, like where the acid is, like, you know, every cell. The only difference, it adds up the voltage.
Right. Yeah. So when we get into batteries, we'll see how a battery is actually a series circuit. Our 12 volt battery has 6 2.1 volt battery cells to make a series circuit. So what we're talking about in circuits, we're going to roll right into batteries because that's how batteries are made. And that's how I can get a 300 volt battery or a 6 volt battery or a 1.5 volt battery. It's all by building series circuits. So here we're seeing, instead of making voltage, we're using voltage, but the same concept. So the key to properly using a DVOM or DMM, as the book calls it, is knowing what to expect to be present at any given test point. So understanding watts. So now let's look at the same circuit and let's do a little watts calculation. Now that we know the circuit's applied voltage and current flow, we can determine the watts. This is critical to understand proper circuit operation if adequate power supply is available. So what is the watts used by resistor number 1?
9.
9. How about resistor number 2?
18.
How about resistor number 3?
9.
9.
You do that.
So what is the total watts used by the circuit?
36.
36.
Isn't that the same watts that we had with one light bulb on the last circuit? Because what is it? The
Yes.
resistance is what controls current flow, and watts is what? Current flow times voltage. So hopefully people are getting a little more comfortable here. And
Mr. Brian, but we're just gonna work with voltage, ohms, and resistance, right? I mean, on amperes, right? Or we're gonna use watts?
We use watts because I use watts in the starter module. So we'll see watts a couple times. If you get into hybrids at all, hybrids use a lot of watts.
Oh, okay.
Both on their scan tool data and other stuff because of how they're measuring power and torque. So it's something you should definitely become familiar with, because as we're getting more electric vehicles and more hybrid vehicles, we're seeing more and more things actually use watts to display values on a scan tool to show how hard we're working or how we're applying horsepower or things like that. And so it is something that used to really not hardly be used at all. That's being used more and more as vehicle technology is changing.
Okay.
Mr. Brian, sorry.
Yes.
My head is just thinking here. So if you're comparing this series circuit to, like, say, Christmas lights.
Okay.
Where do the resistance go there? Are there any resistances at all in the Christmas lights?
Yeah. Every light bulb is resistance.
Every light bulb is resistance?
Yep. Every light bulb is a load.
Every light bulb
So in talking about the wattage,
and load.
so you're adding all the light bulbs, individually and come up with a wattage? I'm sorry.
Exactly. So, new light bulbs, now if one goes out, they don't all go bad. They don't all stop working, right?
Right.
But new light bulbs are what? Light emitting diodes, aren't they?
I'm sorry, what?
So light emitting diodes, and light emitting diodes have a fairly
Light emitting diode.
high resistance, so they don't flow much current, but they put off a lot of light. So I'm able to run them in parallel to each other. In the old days, when light bulbs, when I was a kid and they were all in series, you had what? I remember the big light bulbs we had on the Christmas tree. Then they came out with the mini lights because they used less electricity. But remember, they used to warn you not to plug two strands in together and how hot the light
Yes.
bulbs would get and all that.
Yeah.
So because we used a fair amount of current, and again, they limited the current flow by how many light bulbs you put in a row because each light bulb's a load. So in order, even though we're starting with 120 volts, you know, if I get, say, 100 light bulbs on a string, what's each light bulb getting? 1.2 volts, right? You know, so you're dividing that down, and then you can calculate, you know, it's going to give you. So yeah, as it breaks down, you are doing it. So every light bulb is a load.
Okay. Thank you.
You bet. So now let's look at everyone's favorite parallel circuits. I heard a laugh. Okay, so let's ask some questions and walk through, and I think Rudy's going to feel better after we do this. Or he'll really have a heart attack, one of the two. So what is the applied voltage to the circuit?
12.
12. How much current is an amp meter number 2?
4.
3.
3, right? Because, right, I can split this into 2 series circuits. So I got 3 amps there. And so what's the current going to be at amp meter number 3 then?
3.
Right. So what is amp meter number 1 going to read? 6. And how about amp meter number 4?
6.
There you go. Right? Because each leg, you remember, current adds, right? Current adds and resistance divides. So I have 12 volts with 6 amps because each leg is flowing 3 amps. What effect did the parallel circuit have on the complete circuit's current flow? Well, it what? Added, didn't it? It increased. How did the effective resistance of the individual resistors change? So as far as the circuit's concerned, is it really acting like 4 ohm resistors, or is it acting like 1 2 ohm resistor?
1 2 ohm.
Right. So my effective resistance of the entire circuit is 2 ohms because I have 12 volts divided by 6 amps is 2 ohms. So the effective resistance of the complete circuit is 2 ohms, even though I have 2 4 ohm resistors. And that's why we don't use Ohm's law up here to start plugging in numbers down here necessarily, unless I know they're equal. But that's why we like to try to go in and do this.
Oh, okay. You know what, in the problems and the exercises, that's where I was getting wrong. I mean, I did it, but when I was trying to check it using the Ohm's law, it didn't come out right. So now, okay, now I understand. Okay.
Everybody does that, Connie. Every class, everybody does that. That's what makes parallel circuits so hard, is you finally get the series circuit rules, and then if you don't use them carefully on a parallel circuit, you go completely the wrong way. And
yeah.
So that's why, even though we've talked about parallel circuits, I've shown parallel circuits, I put these PowerPoints in on the testing side, and I also sent the handouts to you guys so you have something that you could, and I made them fillable PDFs so you can fill them out on a computer or you can print them and play with them or whatever. But it's something to refer to. So now, continue from what we learned on the last slide. What are the expected voltages at the following test points? So what is DVOM number 1 going to read?
Where's DVOM? Oh. 12.
12, you got it. Because I haven't used any voltage. I've come down here, and as I come to ground, I don't have another load. It's my only load. It has to use all my applied voltage. That's a series circuit rule.
I lost you. Hello.
I'm here.
Okay.
Am I still here?
Yeah, no, you're there.
Okay, I don't want to lose anybody. Okay, so what's DVOM number 2 going to read?
12.
12. Right? Series circuit, 1 load, it has to use all 12.
Yes.
What's DVOM number 3 going to read?
Two.
Zero.
Zero.
Zero, 'cause
Oh,
ground.
yeah, it's in the ground. Two
Yeah,
ground.
0 volts, right?
The
So
ground,
the ground, we've already used all of our 12. We didn't get any change
zero,
back, right?
Oh, we don't have any.
yes.
So it's zero.
Does the voltage drop match the total applied voltage?
Yes, it does.
Yes.
Yes.
What is the watts consumed by each load?
Each times.
36, right?
Mm-hmm.
36 per branch.
Right. So what's the total watts consumed by the circuit?
12 times 3, 36.
You add those two,
72,
right?
right?
72, yeah.
72.
12 times 6, or just add those two, however you want to get there. Now, doggone it, I thought I fixed the timing on this. So ignore my red line for the moment. So this is, it doesn't
Mr.
get any harder than this, really.
Could you go back to the previous one? So I can take a picture of it. Thank you. Thank
Where
you.
you get the 36, sir?
There is also a recording of this session, guys.
Yep, and the PowerPoints are up on Canvas. Try to touch all the bases I can. So now, this is a series parallel circuit. So I have resistance up here, I have resistance here, and I have resistance here. The red line I superimposed, I meant to have timing in it, and it didn't, I didn't get it right. So when solving for unknowns in a series parallel circuit, knowing a few rules can be helpful. One rule is that if two resistors of equal value are in parallel to each other, their effective resistance is cut in half. By knowing this rule, this becomes an easy problem to solve. So if I have two 16 ohm resistors, the effective resistance for the circuit is what? 8 ohms, right? So now this is like having a series circuit with an 8 ohm resistor instead of a parallel circuit with two 16 ohm resistors. Everyone following what I just did?
Yep.
No. Could you repeat that again?
You divided by 2.
You just
Okay.
divided by 2, right?
Yeah, because
So I
you
have
have 16.
this circuit, and in order to figure out the voltage drop across the first resistor, I have to figure out the total resistance of the circuit. So I can
Okay.
figure out the total current flow, right? So I have two 16 ohm resistors here in parallel,
And then you divide it. That's why you
right?
have 8.
So their effective resistance is cut in half, right? So two 16 ohm resistors is like having one 8 ohm resistor.
8. Mm-hmm.
That's right.
Now, this becomes pretty simple. So if I have 4 ohms here and 8 ohms here, now I can figure out the total resistance for the circuit, so I can figure out current flow, right?
Mm-hmm.
So now that we have effective resistance for the complete circuit, the total effective resistance is 12 ohms. These are still 16 ohm resistors. I just hit them for right now so you can understand how I'm using the trick. What is the current flow for the entire circuit?
1 amp.
Amp.
1.
Oh, 1,
So amp meter 1 and 4 are both going to read 1.
1 amp.
And
What is the voltage at the following test points? DVOM number 1, how many volts is it going to read?
12.
12.
Well, take a
4.
look at where the black lead
4.
is.
3.
It's 4.
Or doesn't it? How do I get my voltage drop? I take my current flow times my resistance, gives me the voltage, doesn't it?
4.
yeah, 4.
Has to be 4. Just remember, current flow times resistance equals voltage, which means I'm using 8 volts down here, right? So DVOM number 4 has to read what?
First, DVOM number 4.
8.
Has to read 8. How about DVOM number 5?
8.
8. How about DVOM number 6?
0.
Okay. How about DVOM number 2?
0.0. 0.5.
No.
Well, it's between ground and that point, right?
Right, it's between, what's the difference between ground and this point?
Oh, it's 8.
Has to be 8 volts because I have 8 volts between this resistor and this resistor, and between this resistor and this resistor, I have to have 8 volts. That way I have the 8 volts to use going across those resistors.
8 times 1.
So DVM3 would also read 8.
Yeah.
Now, what is the current flow for each leg of the parallel circuit? Well, now to figure out the current flow, what do I need to do? I need to treat them each like a series circuit, go back to my 16 ohms. And if I take 8 volts divided by 16 ohms, what's my current flow?
2.
You went the wrong way.
That's the one that's 0.5 amps.
Oh yeah, 0.5 amp.
0.5, right?
0.5.
Which makes sense because I had 1 amp here. I split it equally. Each side gets half an amp.
Oh.
So that's about as hard as it gets right there. And I don't ask you these questions on tests. We got 6 of them in a homework is all. But you see how I use that rule of being able to basically convert it to a series circuit to figure out the current flow and then go back and solve the legs individually. So that's why I put this in the PowerPoint, and that's also why I kind of walk through and you can see how we got there. Did these exercises help you guys? Or just
Yes.
Yeah.
So resistance testing. So there are 2 ways of testing for resistance. An ohm meter is best for testing a component against specifications provided by the manufacturer. It's not effective for testing resistance in wiring. The component being tested must be isolated from everything else so the results will not be accurate, and the meter may also be damaged. So if I'm going to use an ohm meter, which is part of a DMM or digital voltometer, to test resistance in wiring, for example, I would need to disconnect the wiring at each end to measure the wire. If I want to measure resistance in a solenoid or a motor, I would need to disconnect it and then basically measure it all by itself. So it's time consuming. It's also not necessarily accurate. Voltage drop is the best way to test a live circuit without disassembly. So this allows me to test something without taking anything apart. Keep in mind, anytime we take something apart, I might damage something. I might accidentally fix it and have no idea what I did. I may break something else or cause a new problem. So the circuit must be complete and have current running through it for the unwanted resistance to be found, unless it's open, in which case I will pick up that I have an instant problem. So here is an ohm meter. And what I'm looking at here is I've zoomed in on a wire and I've taken all the strands apart and twisted just one little strand together. And my ohm meter has 0.4 ohms. And to put that in perspective, GM says that if it's 5 ohms or less, it's not a problem. But yet I'm here to tell you, we're not going to do much work with that little strand. I'm certainly not going to run a motor with it. I'm not going to have a light bulb light up with it. Our power door locks aren't going to work. None of that's going to happen. But if I follow the factory procedure and disconnect both sides of the wire and put up my ohm meter, it's going to say it's good. So this is why we don't use an ohm meter for testing this, because an ohm meter really only tells, is it connected? It doesn't tell me if it's any good. It doesn't tell me if it's going to work. All it tells me it's connected. And even if I use an ohm meter to test a sensor or an actuator against a manufacturer specification, it only tells me that it's electrically okay. It still doesn't mean it's going to work. So we always want to try to test things when they're supposed to be working or when they are working.
We lost you again.
You lost me again. I wonder why we're losing my audio. Is everyone losing my audio?
No.
No, it sounds good.
You're good.
Okay. I think it's just you today, Connie.
Your sound is good.
Okay. Yeah, I usually don't have problems. I got a pretty good mic in here and everything else. So I know I'm a little echoey because we're remodeling, but
It must be just a signal here at the house or something. I don't know.
yeah, well, you said it twice. I want to make sure because if it was me, I need to start checking connections or see if something happened there. And I got to play with that after we get done with class because I don't want you guys experiencing.
I had the same thing too. I lost you for a second there.
Yeah, mine.
Oh,
went
I'm
up.
glad I'm not the only one.
Oh, your own.
Maybe it is me. I'll double check things. Sometimes the USB connectors get a little corroded. Okay, so circuit function. When current flow through the bulbs heats up a single strand, then the strand will heat up, resistance will rise, and voltage will drop across the strand. So here I have the wire, example of the wire that we just had on the last picture. So if I have the wire, in this case on the ground side, and there's only one little strand connecting it, I would use a good part of my voltage across that strand, because as that strand heats up, then the resistance will rise and the voltage will drop across it. And so my light bulbs might not light up, but yet it's because I have a single strand. So if I used an ohm meter between the light bulb and ground, it would test good. Also, if I unplug the bulb and look for both bulbs and look for voltage, I'd see voltage there. I'd see both power and ground. So that's why we always test things when they're connected, when everything's hooked up. We should never disconnect something and then check for power. We should never disconnect things and then ohm out a wire to see if it's good, because it's not going to give us the right answer. So we always want to test things dynamically when they're connected, when they're working. So an ohm meter will tell you which of the following.
Number one?
Number one.
Number one, yeah.
That's it. I don't care what the book says. I don't care what anything else is. All it tells you is that it's connected, period. It doesn't tell you it's good. It doesn't tell you it'll work correctly. And the wiring is good. It's kind of like saying the circuit is good. I was just running out of things to put there. It doesn't tell you that it's good or that it'll work. It just tells you it's connected. And that's a real important distinction. Going back to Dell on the flow charts, a lot of flow charts use an ohm meter, and they have you check resistance and things and then assume it's good because it's written by an engineer. And in the field, we find that that's not the case. So what we want to do is actually test things dynamically, test things when everything's connected. And that's really how we find the problems. So circuit tracing. So I have some exercises here. Normally we use highlighters with, so I missed being in class because normally you guys get to color today. But I have a red wire, which is a power source. Yellow is going to be a switched power. Blue is a switched ground. Green is ground at all times. Orange would be varying voltage. And I can circle the load. So I have a picture here. And this is a horn circuit. So what I have is I have an integrated power module, and I have a horn relay, and I have some circuitry inside the integrated power module. And I have two horns. So here's a parallel circuit. I have a ground over here, which goes to my horn switch on my steering wheel through what's called a clock spring. Now, a clock spring, if you guys were in brake and suspension class, you guys have already learned about these. But they are a device that mounts between the steering wheel and the steering column and allows you to turn the steering wheel about 4 times, back and forth, and it'll maintain electrical connection. And so it's just kind of a coiled piece of wire. And then it comes into the computer. So as I figure out what should be what on this, I can start with my power source. And then I can highlight that in red because red is power. There we go. And so there's constant power. The relay, the switch is my control device. My yellow is my switched power. There's my loads. And there's my ground. So since this is switch power, when the control device is open, I'll see ground here at pin 87. And when the control device closes, I will see power at pin 87. And this is why relays are a great test point. Because at the relay, we'll see that I can not only test, am I getting power from the fuse? I can test to see if the switch is able to close and send power out here. But it also tells me if I have ground here that at least one of these horns is still connected. Because if this wire was broken here, then I'd never see ground there, because the ground from here that goes through the load, that potential would not be able to reach here. So this is true for fuel pumps. It's true for anything with a relay, electric cooling fans, AC compressors, you name it. Instead of having to go get to all the different places, like the horns might be buried behind the bumper and it takes me an hour to get there. But if I test it at the relay, I can verify, do I get power in when the switch closes? Do I get power out? I might be able to use a tool and apply power here to see if the horns come on. So I have a lot of options.
Just to be clear, when you're doing these tests, you're pulling the relay and testing the points, right?
No, I'm cheating and using a tool that I'll show you.
Oh, I didn't consider cheating.
Well, the reason why I don't want to necessarily pull the relay is I want to also monitor the relay function at the same time. So if I didn't have that, then yes, I would have to pull it out and I could check for power here. I could apply power here or see if there's ground. And I'm going to draw out this other side of the circuit in a second. But the problem is that I've seen open circuit potential. So for example, I could see power at pin 30. And if I power this up from another source, I really haven't tested the integrity of the connections at the fuse or the connections through here, because all I'm checking is open circuit voltage. By using this to power it up, and I can certainly do that with a jumper wire between 30 and 87 and just throw a little jumper in there and see if the horns go off. And then that would be testing the power. But a lot of times people use another source and they're not really testing that. So I like to do it with the relay in, and I'm actually going to show that tool. I believe I have it later on in the PowerPoint presentation here. I'll double check. If not, I'll get it put in over the weekend. And I did buy some of those. So that is, it's a little relay tester. And what it does is you take the relay out, you plug it in, and then you plug the relay into the top of it. And then it has the little tabs that are numbered along the side of the tester, so I can do all my tests there with the relay in place. So I can actually watch the relay work. I can apply power ground. I actually did a video using the tester when we get into cooling systems for the electric cooling fan, and I have a lab assignment on that. So you'll all get to see me use that tool along with the power probe that I demonstrate. So I did do a lab using both those techniques. But I will show you the tool in this presentation. So now if I look at the control side, now I have power, I have a load. So now my relay is the load. I have a switched ground and a solid ground. So now when the horn switch is closed, ground is applied all the way through here. And now this is the load, creates electromagnetic force and pulls this switch over to pin 87 and allows the horns to be energized. So if this is not pushed, then I would see power here on pin 86. And pin 86 gets ground in order to energize it. And so again, it allows me to test, am I getting a good ground signal here to turn on the relay? Because if I just unplug it and check for a ground signal, that's not really loading the circuit. And so that's why we always try to test things together. And relays just you'll see as we go through different schematics throughout the class, you'll see me go back to relays because they just make a great test point and they're normally easy to get to. But the blue is my switched ground. So it's only going to have ground when the switch is closed. The rest of the time, we'll probably see power there. So you can see my horn actually has two sides of the circuit. It has the switch side here, which goes to my main load, my horn. And then I have a load inside my relay. So these are what? Parallel circuits, aren't they? One parallel circuit, this is the load. The other one's, it's the horns. And so when we say the horns don't work, to just jump in and go, well, I think it's a bad horn. It could be a bad clock spring, could be a bad horn switch, could be a bad integrated power module. That sounds expensive. That's kind of like a rear SAM. Could be a blown fuse. It could be a bad wire here. It could be two bad horns. It could be a bad ground at G104 where it got corroded or the bolt came out, so it's no longer connected. It could be a lot of things. The easiest place to test everything at once to get a direction is at the relay, because that's kind of a high level test. I don't think the relay's bad, although it might be. What it does, it allows me to split the circuit into all 4 different parts. And now I can see which of those 4 parts is not working. So I have a direction to go to find the problem. Does that make sense to everybody?
Yes, and I would like to underscore something. I've encountered several videos on YouTube where a customer brings the car into a shop and there's various complaints. Things are not working. Among them is the horn that's not working. And usually this person that is troubleshooting says, well, horn circuit is one of the easiest to troubleshoot, so let's go over there. And usually when you have multiple issues happening, it all probably stems from the same root cause. And
Yes.
by monitoring and going through this similar schematics like you have here, he actually finds like a bad ground usually or something, because that may be a common point for multiple components that, and he fixes the whole thing by doing
Correct.
it.
And that's the power of looking at wiring schematics. Is if I have multiple systems that aren't working, the question is, do they share a power or a ground? So, you know, if they're related systems, they may share power. They may share this 25 amp fuse. And I could go to power distribution schematics and see everybody who uses the fuse. I could also go to my ground distribution schematics and see everybody who uses G104. And so very quickly I can figure out, wait a minute, if everybody that uses G104 is what the customer's complaining about, it makes sense to go test G104, right? It makes sense to go see, did someone forget to bolt it on the car when they worked on it? Did the wire break or get eaten or whatever? So yeah, absolutely. And the horn is an easy circuit to diagnose. And so we do that quite a bit. If I have multiple systems that aren't working, I'm going to diagnose the one that's easiest first, thinking that they're all probably related. So I'm going to go to the one that has the easiest test points and is the easiest to check out. So that's a great point. But hopefully you guys see the logic or the wisdom of, instead of starting at the fuse and kind of working in a very linear approach, or instead of jumping around thinking, I read online the clock springs go bad all the time, or I read online and the horns go bad all the time. It makes sense to go to a central point where now I can divide this into 4 parts. I can quickly figure out which of those 4 isn't working. And if they're all working, it's a bad relay.
So, Mr. Brian,
yeah,
based on what you just said and our quest to save time, would I be right in saying that the first thing I do is jump out pin 30 to 87, and if the horns work, then I've got half of my circuit is just fine, and it's just the control side that I have a problem with?
Bingo. You got it. And then if you got power at pin 85, you know the problem has to be what? Through here. Now, do I really think it's the integrated power control module, or is it easier to check the horn switch or the clock spring? I got a connector here, C201. It is right at the bottom of the steering column. That's probably might be the next easiest place to test, because that way I don't need to take the steering wheel off to get there, right? Or take the airbag off. On the other hand, C201 might be real hard to get to, and it's easier just to take the airbag off to get to the horn switch, where again, I can check continuity through the clock spring. So, you know, it's each car is a little different, but you're on the right track. By going to the relay, you just cut your work in half. You figured out what's not wrong. And then once you realize you got power at pin 85, hey, the problem has to be in the control side. I can't check the integrated power module other than what? Applying ground. So I could go to C201 and apply ground here. The horn should beep. I could go to pin 2 of connector 4, apply ground here. The horn should beep, right? So that's how we test the module. If the module has good power and ground, and I apply ground here, and it doesn't, and the module doesn't put ground here to energize the relay, guess what? The module's bad. Modules are always tested by exclusion. We prove everything else is good ergo the module's bad. So if the module has power and is getting the correct input, but is not giving us the correct output, then the module has to be bad. So you got it right. Yeah, jump on 3087 and you hear the horns make noise. You don't need to buy horns.
Thank you.
You bet. So I do have a little sheet in here. Talks about resistance testing, limitations, and alternatives. And this is in the PowerPoint. Talks about using voltage drop tests. If you're not sure what a voltage drop test is, by the end of class Monday, you will know, because I got voltage drop exercises in the packet I sent you guys, and we're going to be doing on in our Zoom meeting, we're going to be doing voltage drop measurements on circuits. And so you guys are going to have voltage drop down by the end of Monday. So this kind of just talks about limitations and some cautions. So I'm going to end this right now because I had people ask me about questions on the parallel circuit. And I want to make sure I get there today and don't ignore anybody who asked for help. Does that sound like a plan?
Yes, Mr. Brian.
Okay.
Mr. Brian, your Zoom meeting today is recorded, because I was looking at yesterday, the Zoom meeting the other day.
Yeah, yesterday I just put up this morning. Today's will either be up end of today or tomorrow morning. It depends on how long it takes YouTube and Zoom to process the video.
Good, because some of your subject you teach, it doesn't go inside my brain.
Yeah. Well, that's why I put the videos up and why I put the PowerPoints up and I put all this stuff up. That's why I take the time to do all that so I can try to get it in your brain.
So my wife is buying me a lot of peanuts.
Oh, I like peanuts. I like the mixed nuts. My wife buys those and I've been eating way too many now that I'm home.
Good for you, but I like lumpia.
There is even a proverb that says the repetition is the mother of knowledge. So, you know, you may need to go back.
Yeah, if you're only 18 years old or 20 years old, I'm already 66 years old.
That's not a good excuse.
You're 66 young.
That's an excuse. Even you go to medical, it's an excuse.
It's a poor excuse.
Well, I don't know. I have a lot of empathy because when I went back after 20 years to do my algebra class I needed for my degree so I could take the job at ECC. And I used to be really good at math. And I tell you what, I would follow the instructor in class. I would see that. And I remember this. I remember learning this. I'd get home with the homework. I might be able to get through the homework. And it was test time. I'd look at it and go, I know this and I can't remember how to do it. So I am very empathetic. And that was a problem I didn't have when I was 30, but I certainly did later on when I went back to school after 20 years. So I am empathetic that we do learn differently as we age.
That's so true.
I do believe you, because if you keep doing it every day, you will know it. Like now, I'm a custodian tech. Now I forget what I'm doing in the Navy right now.
So which question did you want me to look at first? I know someone emailed me with one.
Mr. Brian, in parallel, the number 9.
Number 9, lucky number 9. Okay. Okay, this is the worst question. I should probably just throw it out. The only way to solve this question really is to plug in a number for E or plug in a voltage and do some math and figure out. So we know we're allowed 1 amp of current. So if I have a 12 volt battery and R1 is 2 ohms, that's going to be 6 amps, right?
Yes.
So obviously 12 volts is way too much battery, right? So if I go to a 6 volt battery, now 6 volts through 2 ohms of resistance would be 3 amps.
Yeah.
So that's still too much because I can only have 1 amp for all these legs and I know amperage adds. So let's go a little lower. Let's try 1 volt. So 1 volt through 2 ohms is how much?
2. 1 times 2.
You went the wrong way.
So how you do it?
1 divided by 2 is?
Wait.
0.5.
5.
So is 1 a possible answer then? because 0.5 is less than 1 amp, right? And can only have 1 amp total. So I got 0.5 on resistor 1. Is it worth solving for resistor 2 now to see if I can solve all of them and get above or below 1 amp? So if I take 1 volt times 4 ohms, how many amps is that?
4.
Ah, you went the wrong way again.
10.
1 divided by
5.
4.
But you said times. You said times. That's why I
Oh,
said
I'm
4.
sorry. Did I?
You said times.
All right. I'm sorry. My fault. I was thinking divide.
0.25.
0.25.
So it's 0.2.
So R3, 1 divided by 6 would be
2. No.
That's the one I was thinking. So
5. 0.5.
Less than 0. Is it 0.5? I need to kick the add machine over. I can't do it in my head. And then if I do 1 divided by 12, I'm going to come up with like
0.08.
8, right?
0.08.
Yeah. So 3 is like 0.17. 2 is 0.25. And 1 is 0.5. If I add all those together, do I get 1 amp?
Yeah.
Yeah. So the answer is 1.
1 volt.
1 volt. So I solved this the first time by just plugging in numbers, right? Let's start with 12. What happens? Do I need a bigger number or a smaller number?
So I'm saying there's no set formula. I mean, there's got to be a set formula to figure it out.
There is. I put the formula in the chat.
Yeah, there is a formula for it.
Oh.
I know, John. I asked John for help with the formula. Helped me a lot.
Yeah, the parallel resistance formula that I showed you guys, where you take resistance total equals 1 of R1, 1 of R2, plus 1 of R3, plus 1 of R4. You add those together, divide it by 1, and that'll give you your total resistance. And from there, you could take your resistance times your volt, times your current flow, which will come up with your voltage. So you can use that hard formula that I put in the PowerPoint.
Yes, that's good.
So that formula will get
It's help.
figure out the total resistance. Now you just take the total resistance times the current flow and it'll give you the voltage. Or you can plug in numbers.
Brian.
Yes.
I know the Ohm's law. My question is, when you go into that diagram that you showed like 10 minutes ago, when getting the watts, you go for Ohm's law first, then you go to watts value.
Okay. Yeah, and we're not solving for
that. So now I know you mix the Ohm's law with the watts value like that.
Yeah, I don't, like I said, the watts value I did on the other ones just to kind of demonstrate, get you guys thinking about how we figure watts and just kind of reinforce that. There's no watts questions anywhere on this homework. So we really won't see much of watts till we get into starters. But did I answer the question on the number 9 for you? Okay.
Yes.
So you have the parallel resistance formula in the PowerPoint. You have it in the chat. And you also have what I showed you, where you just plug in a number and do it that way. So there's a couple different ways we can get there. Is there another question on here, people?
Or Mr. Brian will just go to the canvas, you said. You can go now.
Yeah. So is there another question on here in the parallel exercise people needed help with?
Now I have got 6 right answers since yesterday.
Good for you.
How about Mr. Brian? I think number 14. I think 14 or 15. Is that okay if you do one more question?
So is it this one?
Well, I have to look at my notes.
Well, I don't want to do the wrong one.
Yeah, number 14. Oh, wait.
Number 14. So I know the voltage.
7, 8, 9.
I know all the resistance. I just don't know the current flow. So,
Oh, number 15. Okay, now we just did number 9. So 14, please. Yeah, 14.
so 14, the one I have up on the screen right now.
Okay.
You're not sharing.
I'm not.
Doesn't show. Yeah.
I'm sorry. I should have had it up. I thought I was sharing on the last one I shared with you guys.
No, you weren't sharing that one.
You need to let me know that sooner.
Well, I didn't know that you had it up.
But the answer is 12.
Well, I did pretty good explaining for not having it in front of me then. That explains the confusion.
Are we 14 or 15? I'm sorry. Are we doing 14 or 15? 14. Okay.
14, yeah.
I have 14 on the board right now. So 14 and here's 15, which you just tell me which one you guys. This one we're solving for voltage. So this is the harder one. This is like the other one. So we can use our formula, right? So I would add R1 to R2, add R3 to R4, and then I have R5. So I have 3 legs. So if I use the formula and use the resistance for the first leg, which would be 1/4, and then this 1/4, and then this right here would also be 1/4. So I got what? 0.75, 1 divided by 0.75.
Okay, Mr. Brian,
Is
you
this
have
that?
R1 and R2?
Is this that question?
Yeah. So 1 divided by 0.75 is what?
Which 0.75?
So what we have.
0.57.
Right. So what I did is I got what? 4 ohms on this leg, 4 ohms on this leg, and 4 ohms on this leg. So the formula says take 1 of resistor 1. So this is the first. 1 of resistor 2, which is my second leg, and 1 of resistor 3. Well, 1 divided by 4 is 0.25, right? And then 1 divided by 4 is 0.25, and 1 divided by 4 is 0.25. So if I add all those up, it's 0.75. So 1 over 0.75 is 3/4. My resistance total is 4/3, or 1.33333. And if I take that times 6, I come up with 7.98, or basically
volts.
And if I put 8 volts in here, you'll find that it works. But that's how we get there using the formula. The other way would have been to plug in a 12 volt. Does that work? No, it's too big. I can plug in a 6 volt. Nope, that's too small. It has to be in between. And I can do that. But the formula just gets you right there.
So, Mr. Brian, in that instance, you add the resistance per branch. You add the 2 and 2. So when you add those 2 branches that are 2 and 2, the rule doesn't apply then when they become all 4s?
Well, you could do that too. I got 3 4s, right? So I could, because this is 4, this is 4, and this is 4. I could do 4 divided by 3, which is going to give me what? My effective resistance.
Yeah.
Which will give me that same
1.3.
That same number, that 1.33333 or 4/3.
So the rule still applies if you add. Okay. I wasn't sure of that yesterday.
It does, because we can do that because each of these legs is its own series circuit. And we know from the series circuit rules that resistance adds in a series circuit. So we're comparing each of the legs. I have 3 legs, all have 4 ohms, 4 divided by 3, 4/3 or 1.333.
So that's very convenient because they're equal.
You get the 8.
Yeah.
So there's 3 different ways, several different ways you can get there. One is kind of a hunt and peck. One is the long formula. One is using the cheat rule that I like. So the good news is that once you guys are done with these exercises, we're pretty much done with math in this class as far as doing any of this. So you don't have a whole session to look forward to that. We kind of get through this, just to reinforce it. Again, repetition and doing it helps you understand it. So then when I refer back to it a week from now or 3 weeks from now or 6 weeks from now and say, remember this rule? This is how we do this. We use this rule from Ohm's law. And even though might be talking about, windshield wipers or whatever. So it's helping you guys with the foundation here. So like I said, this is the only module I do all this math and all this kind of stuff in.
Mr. Brian, I thought you were going to touch on the series parallel circuit.
Yeah.
I
Yeah.
think
Because there's still one exercise that's due, I believe, Monday, right?
Yep, and I'll touch on that again a little bit more today. We can do that. So let me pull this up. So I did the first couple of them yesterday, I think. So I'll go through this again. So here I have a resistor in one of the legs, in this case, the positive leg. And then I have two parallel circuits right here. Now, if I look at R2 and R3, they're both the same amount of resistance.
Mm-hmm.
So their effective resistance is going to be 2 ohms.
Okay.
Right? So if I take my 12 volts, divide it by 3 amps, the circuit has to have a total effective resistance of 4 ohms. Are we good with that?
Yes.
Okay. So my effective resistance of these 2 legs is 2 ohms. So if I take this 2 ohms away from the 4 ohms I have to have, or I'm sorry, yeah, for the 4 ohms I have to have, what does R1 have to be?
2.
2 ohms. Okay.
And so I put 2 there. Now here's question 2, which is, again, now I have a resistance on the negative side. I have a 4 ohm resistor here and a 4 ohm resistor here, 12 volts here, and 3 amps of current flow. So if I take my 12 volts, divide it by 3 amps, I come up with 4 ohms for my total.
Mhm.
These are in parallel, right? I have a parallel circuit here to here. So they're both the same size resistors, so I can use my tool and divide these by 2. So this has an effective resistance of 2 ohms. So I know the circuit has to have a total of 4 ohms. So I take the 4.
Oh no, we lost you.
Lost you again.
You lost me.
Please,
You
Ellen.
did with R1, R2.
Okay.
Am I back?
Yeah, you're
Too
on.
fast.
You're back now.
Yeah, that really happened.
Okay.
Okay, good.
Well, good to know, because I moved things around and some stuff got plugged and unplugged, so something might not be a little happy.
So go back to the 2 parallels. You said R1 and
R1
R2.
and R2 are both 4 ohms.
Mm-hmm.
For a parallel circuit, I can use my tool and divide the effective resistance is going to be half that. So my effective resistance is only 2 ohms. I know the circuit has a total effective resistance of 4 ohms. So if I take 4 and subtract 2, R3 has to be
2.
2. So this is the exact same question in number 2 as we had in number 1. The only difference is instead of the resistor being on the positive side, it's on the negative side.
It's negative.
Okay.
Okay.
Say again, Mr. Brian.
So now things look a little trickier, but they're not. So now I need to figure out current flow, which is fairly easy because I know the applied voltage. And I have what? I have resistor 1, which is 2 ohms, resistor 2, which is 4 ohms, resistor 3, which is 2, and resistor 4, which is 2. Well, wait a minute. Don't I have a parallel circuit here? Isn't R3 and 4 in a circuit parallel to R2? And since resistance adds in a series circuit, 3 and 4 add together to make a 4 ohm circuit and a 4 ohm circuit. So now can't I use my trick and know that the effective resistance for this loop is only 2 ohms? So if I have 2 ohms here and 2 ohms of effective resistance here and 12 volts applied, what's my current flow?
3.
3. You got it.
Okay, can you go back when you were explaining which were parallel? Parallel is 2 and 1, right? Those are the parallel?
Well, in this example, my parallel is my 2 and
R2,
3 and 4.
R4.
In this example, it's my 1 and 2 are parallel. In this example, it's my 2 and 3 that are parallel, right? So you can kind of get past here, and if I snip here and snip here, I have a parallel circuit. If I snip here and snip here, I have a parallel circuit. If I cut the wire here and here, it would be a parallel circuit, and they're equal. So if I look here, this is one that we want to find voltage. I have what?
4 plus 4,
So
8.
I have 8 ohms here, right? And the parallel circuit also has 8 ohms. Is that the same?
Yes.
So I could what? Use my trick and I have an effective resistance of 4 ohms.
Mm-hmm.
So 3 amps times 4 ohms is going to be how many volts?
12.
There you go. So this one looks more intimidating, but wait a minute. R2 is 8 ohms. R3 is 2. R4 is 4. R5 is 2. Well, 2 plus 2 plus 4 is 8. Do I have 2 equal parallel circuits now?
Yes.
So an 8 ohm circuit, their effective resistance in parallel is going to be 4 ohms. And we know that R1 is 2 ohms. So 2 ohms plus 4 ohms is 6 ohms. 12 divided by 6 is how many amps?
2.
There you go. And here's the last one, and I'll leave it for you guys.
Aw.
I gave you guys 5 out of 6 here.
Come on, Mr. Brian.
This is the same thing we've already done a couple of times. And this one's easier, just figuring out current flow. So is R1 is 12 ohms. R2 and R3 are both 6 ohms.
Yes.
Does that make them parallel circuits?
Yes.
So their effective resistance would be
2.
2.
2. If
No,
I have
wait,
No, it would
wait.
be
1.
half of the each of the
12 ohms
branches.
here, the effective resistance on this parallel circuit is
Wait.
12 plus 18.
what? No, we shouldn't be adding. We
No,
got
you have 12 per
12
branch.
here.
Mr. Brian, they're not the same ohms.
yeah, they are. 'Cause
R1 and R2?
R2 and
No.
R3 are 6 ohms.
R2 and
Well, then
R3.
6.
This whole leg equals 12 ohms, right?
Yes.
And doesn't this leg equal 12 ohms?
Yes.
So this leg and this leg are parallel circuits, correct?
Yeah.
With the same amount of resistance, correct?
Yes.
So resistance
No,
divides.
R1 is.
The
R1
effective resistance is 6
They're not the
ohms,
same.
and then the current is 2.
Right.
R1
Well,
is
hold on. Don't forget about R4 here.
Wait, everybody's
Effective
talking all at
resistance.
one time.
My effective resistance, you're correct, is 6 ohms for my loop plus 2 ohms for R4 for a total of 8 ohms. So if I take 12 volts and divide it by 8 ohms, what's my current flow?
Mr. Brian, the question says R1 is 12, R2 is 6. So they're not the same for parallel.
But R3 is
Well, look at where they are.
Well, R2 and R3 are parallel to R1.
right because
Or
it's
by
the
itself.
same- right, because this is a circuit. From here to here is a circuit, and from here to here is a circuit. They're parallel circuits. Each are a series circuit. So since resistance adds for total resistance in a series circuit, even though R2 and R3 are different resistors, I can treat them as one resistor for the point of the circuit, because the total circuit resistance for this circuit is the same as the resistance for this circuit. They're both 12 ohms. That's why I'm able to do the trick.
Oh, I thought the parallel series here, the parallel circuit is the R4 and R3. I'm sorry, the
R1 and R2.
what's the first one?
Yeah, R1 and R2. I thought those were parallel.
R1 and R2 are parallel, and the other R3 and R4 is series.
No, see, that's great you said that, because this goes back to what I talked about, what we need in a circuit. I need a power supply, conductors, and a load. So I start with a power supply, I have my conductors, a load, and I'm going to get back to my power supply. I have a power supply. I got my conductors, 1, 2 loads, and back to my power supply. Now, both of these circuits share this, so I can treat this as part of my power supply. So if I look, if I go from here to here, there's a parallel circuit. I go from here, what? To here is another parallel circuit. So this loop is parallel to this straight line. So that's why I'm able to add my R2 to my R3, because this is one circuit. There's no power or ground between these two resistors. So that I can treat them as one because they're in parallel to this circuit, even though it only has one resistor. Does that
Okay, now I'm totally confused. I am totally confused.
The way that I think about it is like where R4, the wire on the bottom, I snip it, and then at the top I snip it. Like in R1 and R2 and R3 would be in its own little series by itself, and then R4 would be by itself.
Absolutely. And that's exactly how I do it when I'm on a whiteboard. I just cut it here, cut it here. Do I have two parallel circuits now? Yes, I do. Is the resistance in each circuit the same? Yes, because this one has 12 ohms and this circuit has 12 ohms. On this circuit, it's two 6-ohm resistors, but it's still 12 ohms resistors. Now that they're both 12 ohms and they're parallel, I can use my rule and cut them in half.
Okay, so I'm looking at the picture and I thought when it says parallel, it will be like going up and down. Sorry.
That just means it's Thursday and you're ready for the weekend.
Maybe so.
There's actually several ways to draw this. If you just extend these lines and put them a little bit different, it's going to be way more clear for everybody. But unfortunately, in the schematics, you see it like this. So.
Yep. Yeah, I could have drawn R2 and R3 right on top of each other, except for I didn't draw this. I got it.
Oh, okay.
R2 and R3, if they were right on top of each other, I don't think you'd be confused. But,
exactly. That makes it clear. So that's the way to look at it, is the way it's drawn and figure it out differently.
Yeah.
Yeah,
so
you can use pen and paper and redraw this same thing. And
right, or use the thing.
Oh yeah, on the Snap-on account, it seems like I can't log in on the regular site. I can only log in on the student.
Okay, you're talking about a different thing. Back on the
No,
subject.
I already signed up, but I can't log in.
Can't you call me on my home phone number so my wife can join us as well?
Oh my goodness. Okay. I think I'm getting it. Mr. Brian.
So what's the answer, Mr. Brian, to this one?
What is the answer? You guys already gave me the answer.
No, we didn't.
No.
Okay.
1.5 is the answer.
What, John?
1.5.
Okay, got to figure it out then, like we did with the others last time.
Right? Well, you think about it, what's 12 divided by 8? Right? If this is 6, is if the effective resistance of this parallel circuit is 6 ohms, and I add 2 more ohms, I have what? 8 ohms.
8 ohms.
And 12 volts divided by 8 ohms is?
Well, I have to use my calculator. Hang on.
I don't want to kick my shoes off.
1.5, yeah.
1.5.
Yeah. Okay.
So I expect everyone to get 100% on this exercise is all I can say.
Well, if we didn't, something is wrong.
Something's wrong between I went over everyone, some of them twice, and I'm going to put this up and you'll see the video of it, and you all were here. So I am very optimistic. A lot of people are going to get a lot of points on this one.